So that's good. Let's jump into chapter 14, shall we? Okay, 14.1 is functions of several variables. Okay, number one, find the domain of f of xy equals the square root of x plus y plus 1 all over x minus 1. Okay, so what are the restrictions on this? Well, the restrictions are that x cannot equal 1, right? And that whatever is under the square root has to be positive or 0. It has to be a non-negative. So this is x plus y plus 1 has to be greater than or equal to 0. Okay. Well, these are both lines. Okay, we can find the region in which these are both true. Okay, so let's solve this guy here for slope-intercept form. So y is greater than or equal to, okay, y minus x, oh sorry, not y, negative x minus 1. Right? Okay, and x is not equal to 1. Okay. So let's see what region we're talking about here in our domain. So our domain is going to be a two-dimensional region, because it's where the domain is with respect to x and y. And f of x, y, you can think of this guy as z. Okay, that's the z function. Okay, it's multivariable this time. Instead of having a linear domain, we're having a region in the Cartesian coordinate system. Okay, so we're going to have this guy here is going to have a y-intercept of -1, and it has a slope of -1. So we get this this nice line here. Okay. That kind of sucks. That's pretty bad too. Let's try this. There we go. Okay, so we've got a line. Okay, and we want everything except for, well, we'll get to that. We want everything that's bigger than this line. Well, if we test the point 0, 0, okay, is 0 greater than -1? That's true. So it's everything above the line that's graphed. Okay, except this line here at 1, when x is 1, we cannot have this region here. Okay, we can have everything else except for that region there. That dashed line cannot be included in my graph. Okay, but everything in this region other than this purple line is a part of the solution set for the domain. Okay, so that's what this domain is. Okay, number 2. Find the domain and range of g of xy is equal to the square root of 9 minus x squared minus y squared. Okay, so my nose is just constantly itching today. Okay, so what can we not have under the square root? Well, once again, we cannot have a negative, non-negative. Okay, so that means that 9 minus x squared minus y squared has to be greater than or equal to 0. Okay, so if I solve this, if I get this in a form that's more familiar, if I were to toss these guys to the other side, I would get x squared plus y squared is less than or equal to 9. Okay, and what is that? Well, that's a disk. That's a disk of radius 3. Okay, that's a disk of radius 3. Oh, okay. So the domain is a disk of radius 3. Okay. And so everything inside, right, of this disk is a part of the domain. Okay. Well, what about the range? Well, okay, so let's say that we're at this point here on the disk. Say that we're at 0, 3, right? Then what would be the function value there for g of xy? Well, g of xy would be 0, right? Because wouldn't you get 9 minus 9 minus 0? Okay, or 9 minus 0 minus 9, and you would get the square root of 0, which is 0. So the lowest value that I could possibly have here is going to be 0. Okay, that will be my minimum value. Okay, when we're the closest to the boundary, well, when we're on the boundary, basically, where it's going to be the minimum value. What about if we're at the center? What happens if we're at the center? The furthest away from the boundary is the center when I'll put 0, 3 here. Okay. When I'm at 0, 0, okay, I'm furthest away, and what's that? That's going to be 3, right? So my domain is basically telling me that, yeah, my range is, my domain dictates my range. And so I go from 0 to 3 on this thing. Okay, for the range. So domain and range. Okay, makes sense? Okay, number 3. Graph the function z equals 6 minus 3x minus 2y. Okay, so we're going to use the x, y, and z intercepts to graph the what? What is this going to be a graph of? Z equals something in terms of x and y. Anybody know what this is going to graph? What type of function?
Is it a plane?
It is a plane. Thank you, Long. It is a plane. Okay, the x and the y and the z are all raised to the first power. It's a plane. Okay. Okay, so to graph the plane. Okay, so let's do that. If x and y are 0, 0, 0, and we'll call this c. So 0, 0, c is going to be where? Where is that point? Well, if x is 0 and y is 0, isn't z equal to 6? Wouldn't that be true? Z is equal to 6, so wouldn't this just be 6? So 0, 0, 6. Okay, what if, excuse me. What if y and z were 0? What if y and z were 0? What would x be? Okay, so we would want something comma 0, 0. All right, let's put in 0. So 0 is equal to 6 minus 3, x minus 2 times 0, right? We would get 6 minus something is equal to 0. Well, that something has to be 6. Okay, you could just basically solve this. and you say 3x equals 6 and x equals 2. Okay, so just plug in 2. There we go. Okay, so that's the, we would call this the x-intercept. This would be the z-intercept, right? The z-int. And then let's get the y-int. The y-intercept is going to be very similar to the what happened with the x-intercept, except this time it's going to be 6 minus 6. But what's going to create the 6 is a 3 there. So this is going to be 0, 3, 0. So we're just using the intercepts to get 3 points on this plane. Okay, so very easy to graph. Okay, so on the x direction, we're going to be out 2. In the y direction, we're going to be out 3. And in the z direction, we're going to be up 6. So we get this nice plane here. Okay, and then I'll just draw the plane. Oops. Okay, let's try that again. Okay, and there's my plan. I'm gonna maybe do a little shading on that. Okay, and that's my plane. Okay, make sense? And you could label your points if you really wanted to. You know, 0, 0, 6 and 2, 0, 0 and 0, 3, 0. So pretty easy. Okay. Okay, number 4. Okay, sketch the graph of g of x, y equals 9 minus x squared minus y squared. Okay, g of x, y is equal. Okay. Did I write this down wrong? Thinking. Yeah, let's do the square root here. Let's graph that. Yeah, that makes more sense. Okay, so what's the graph of this thing going to look like? Well, let's make that g of x, y into just one variable. This is going to be z equals the square root of 9 minus x squared minus y squared. Okay, so let's let z equal 0. Okay, so when z is equal to 0, okay, that's going to be a trace. This is the trace in the xy plane, right? When z is 0, so it's going to be the trace in the xy plane. What's this thing going to look like? Let's draw the graph out here. Okay, let's see what's going to happen at 0 when z is equal to 0. We get square root of 9 minus x squared minus y squared. Okay, and then let's square both sides. We just get 9 minus x squared minus y squared equals 0. And so this is x squared plus y squared equals 9, which is a circle of radius 3. So that's kind of cool. 1, 2, 3, 2, 3, and we're going to get a circle. Okay, a nice circle of radius 3 here. Okay, makes sense? That's the trace. That's the slice. Okay, that's a slice in the xy plane. Okay. Now let's let y equal 0. Okay. Let y equals 0. See what happens here. So z equals the square root of 9 minus x squared. Okay. So when y is equal to 0, that's going to be the trace in the xz plane, right? This is in the xz plane. That's the trace in the xz plane. Okay, so let's figure out what's going on here. Okay, this thing, if I were to square both sides, I would get z squared is equal to 9 minus x squared. And so I could toss the x to the other side. I would get x squared plus z squared equals 9. That again is also a circle, but in the xz plane. Okay, however, the original here, okay, the original, okay, is only the top half of that circle. It's only where z is positive, because there would be two parts to this. If I were to solve back for z, I would get z equals plus or minus the square root of 9 minus x squared. And that doesn't, this guy here only accounts for the positive of that and not the negative. Okay, so this is I'll put a little positive sign in front of there to say, hey, that guy is the positive, which means he's the top half of the circle, not the bottom half. Okay, so we can have the top half of the circle, okay, in the xz plane. That's the top half of, okay, nice. What happens if I let z equal, what happens if I let z equal 0? I'm sorry, not z. Let's let x equal 0. Let x equal 0. Well, that's basically synonymous to what we just did, right? And so we would get z equals the positive of the square root of 9 minus y squared. So this should just be another circle, but in the, or another half circle, but in the but in the yz plane. Okay, so where's the yz plane? Again, this is xyz. Okay, so where's the yz plane here? Well, it would be this guy here. It's kind of hard to see, but we would get that guy. Okay. To be, it's in purple. I don't know if you can see that or not real clearly, but okay. And so we've got this meeting point at the top here. Okay, for those, and that's another half circle. So we're getting this kind of dome shape, this half dome. Okay, and which should make sense because if you think of z equaling the square root of 9 minus x squared minus y squared, well, if I were to square both sides here, again, think of that as the positive, right? The positive. If we were to square both sides, I would get x squared plus y squared plus z squared equals 9, which is a sphere of radius 3. But I only want the top half. This is the top half. So looking at our traces, that concurs that is the top half of a sphere of radius 3. Okay, so this is the top half of a sphere of radius 3. That's the graph of that thing. Okay, let's talk about level curves. Okay, so the level curves of a function f of two variables are the curves with equations okay, f of xy equals k, okay, where k is a constant. K is a constant. Okay, so these are, think slices parallel to the xy plane. Okay, they're slices parallel to the xy plane. Now, are they traces? No, because a trace is just when z is equal to 0. Here z is equal to a constant. Okay, basically you're saying z is equal to k, which means that let's look at our dome again. Okay, here's my dome, right? And so what would be my level curves? Well, for any z value, I would have these level curves. That's really good axes there. Okay, for any z value, positive or negative, okay, I would have a level curve at that z value. So in the case of a sphere, okay, these level curves would all be circles. Okay. Now, if you look at this top down, right? If you look at a bird's eye view here, what are you going to get? Think of this like you're going to get concentric circles, right? Okay, and this should be reminiscent of something called the topographical map. Right, so if you're looking down, right, this is the XY plane, okay, down here, and we're looking down from above, okay, Z is coming out right here, okay, Z is coming out right here, where we would see concentric circles for various levels of K, right, for various values of K. So obviously when K is equal to 0, that's my trace in the XY plane. So K is equal to 0 is this guy, boom. What if K was equal to 1? Okay, K is equal to 1. Oh, that's this guy here. Oh, what if K was equal to 2? Oh, at Z equals 2, that's this guy here, smaller circle, right? What happens when K is equal to 3? Well, then I just get a point. If this was, you know, the thing that I was working with before, if I had x squared plus y squared plus z squared equals 9, then, right, when K is equal to 3, right, if z is equal to k here, if we were to solve this for z basically, okay, but we let z be a constant. If we let that to be 3 squared, which is 9, then the whole thing would become x squared plus y squared equals 0, which is a circle of radius 0. Which means that at the very top of this thing, I have a circle, that slice, okay, that slice, which we're calling now level curves, okay, on this topographical map, okay, that would just be a one single point. Okay, so hopefully that kind of makes sense. Okay, let's give a better definition of this. Okay. A level curve is the set of all points in the domain okay, xy, such that f takes on a given value of k. I should probably say f of xy, just takes on a given value of k. Okay, it shows the graph of f at a height, in quotation marks, of k. Okay, so if we always make the z-axis the vertical axis, then we can think of it as a height. Okay, so think of topographical maps. Okay, let's talk about a certain function here. Okay, this function comes to us from business calculus. Okay. So this is comes to us from business. This is called the Cobb-Douglas production function. That rhymes. Cobb-Douglas production function. Conjunction, junction, what's your function? Okay, yeah. Okay, PLC. Okay, so the function with respect to L and C. Somebody have a question here? Oh, okay, PLC is equal to beta, okay, okay, I guess I can just put beta as beta. Beta times L times alpha times C times 1 minus alpha. Okay, I'm just going to let beta be lowercase b in this case. It's fine. Okay, where alpha goes from 0 to 1. Okay. Where P is equal to the total production value. Usually it's for a large corporation or for like even a nation. These are, we talk about, the production, value of a nation for the year. These are like gross domestic product type of things. Okay, so total production value of a year, okay, for the year. Okay, it is basically divided into two categories. One is the labor hours worked for the year. Okay, and they have kind of an inverse relationship. And the amount of capital invested. Invested. Okay. I mean, the exponents have kind of an inverse relationship. But if you invest more capital, you're going to make more money. If you got more labor, you're going to make more money, more total output of production. Okay, and this is called the Cobb-Douglas production function. Okay, so let's look at PLC. This is a multivariable equation. Okay, is equal to 1.01 L to the 0.75, C to the 0.25, okay, models the production in the US for the years 1899 to 1922, when they first came out with this stuff, okay, about 100 years ago. Okay, so okay, let's look at this for a little bit. Let's use the function. Okay, let's use PLC equals 1.01 L to the 0.75 C to the 0.25 to A, find, okay, the production when we have 147, and these are usually in millions, okay, millions of labor hours and $208 million, okay, so 147 million labor hours, $208 million of capital invested. Find what happens when we get that. Well, we just plug it in. Okay, this is 1.01, 147 to the 0.75 times 208 to the 0.25, which comes out to approximately 162, okay, million production units. Okay, this usually is, you know, dollar hours. Okay, labor hours and dollars, so dollar hours, which is kind of a weird unit, but it is what it is. Okay. Okay, let's plot the level curves here. Plot the level curves for PLC is equal to 1.01 L to the 0.75. That's labor. Capital 0.25. Okay, so let's plot the level curves here. And so what is it saying? It's saying that we want this thing to equal K, different values of K, different values of constants, right? Okay, so the variable P goes away. And we're just gonna have two variables, L and C, and so we're gonna plot this on an L versus C graph. See what we get here. Okay. Okay, so the idea here is that I'm going to get 1.01. This is L to the 3/4, C to the 1/4 equals K, right? Okay, I would like to not deal with fractional exponents if I don't have to. So I'm going to raise this whole thing to the 4th power and this whole thing to the 4th power. That's good, that's good. This is 1.01 to the 4th power. Okay, this is L to the 3rd power, C to the 1st power, I'm just gonna leave it as C, is equal to K to the 4th power. Okay, and so what do I want to do here? so I'm going to solve for C. I'm going to say that C is equal to k to the fourth power over 1.01 to the fourth power L to the third power. Okay. So we can see that we're not dividing by a whole lot here. This 1.01 to the fourth power, that's pretty close to 1. 1.01 to the fourth power is pretty close to 1. And so we can see that there's kind of a relationship here in that this k to the fourth power, that's just a constant. Does that make sense? Okay, that k to the fourth power, that's just a constant. Okay, but we can kind of see that if you take 4 k's, multiply them together, and divide by 3 l's, you end up with 1 c, right? You kind of end up with that 1 c. So there's kind of an inverse relationship here in that as L increases, as L goes up, C decreases, right? And vice versa, okay? As L decreases, C increases, right? So they have kind of this inverse relationship between each other, okay? And so they're always going to be, I can basically say that, you know, we roughly have C times L cubed is approximately k to the fourth power, right? Okay, it's approximately, not equal. Okay, it's approximately, because it's 1.01 to the fourth power is like 1.04. Okay, it's close, it's close. And so what I'm going to say is I'm going to say that I'm going to approximate this to say, hey, well, I've got 1 of these guys and I've got 3 of these guys equals 4 of these guys. And so when does that relationship hold? Well, that relationship holds, okay, only, okay, this relationship holds only when again, and this is a constant. You have to think of this as a constant, right? That's a constant. That's not moving. But this relationship holds, okay, when C is approximately equal to L, which is approximately equal to K. So when all these are approximately equal, then this relationship holds. Okay, C is approximately equal to L, because if you were to replace L here with K and C, you would get L times L cubed is equal to L to the fourth, which checks, right? If you just, we're just saying in a general sense that this relationship holds because of the nature of the function. And so when we go to graph this thing, okay, we can use this idea that C and L, okay, are basically the same number, okay, but just written a little bit differently in terms of, you know, C is approximately L, which is approximately K. Okay, so the thing is if we kind of get rid of this guy, we think of it more like this, that we have C is equal to K to the fourth over L cubed. Okay, But when they're all basically equal to each other, this I'm gonna say is a constant. Let's let k equal, this is just a constant. K to the fourth is just a constant. This is a constant. Okay, so what does this function behave like if that's just a constant? Again, it's a constant where k equals some value. Well, it can't be equal to 0 because then, well, it could be equal to 0 actually. If we let it equal 0, then the whole thing just goes to 0. Okay, where if k is equal to 0, the whole thing goes to 0. Okay, that's not very helpful. Okay, the whole thing goes to 0. Okay, but what if k was equal to, say, 2? Okay, what if k was equal to 2? Right? What would this look like? Well, it would look like c is equal to 2 to the fourth is 16, right? 16 over L cubed, right? L cubed. If you think of this in terms of x and y is equal to 16 over x cubed. What does that look like? Okay, well, that looks like a rational function. This is a rational equation. Okay. And so we're saying that, you know, y is approximately equal to L, which is approximately equal to k. So for a certain value of k, okay, L is approximately equal to C, and which is approximately equal to K. The idea here is that when we go to graph this thing, the L versus C graph, okay, what's this thing going to look like? Okay, what's this thing going to look like? Well, okay, it's going to be these rational curves. Okay, so if we think of this in terms of hundreds, 100, 200, 300, okay, if we have 100 here, right? So, okay, for various values of k, okay, for various values of k, how are we going to, what's the difference? Well, the only difference is the constant that's on top. Okay, that's the only difference here is the constant that's on top. Okay, and so again, the constant or the value, the number, we'll say 16 in this case, is equal to x cubed times y, right? X cubed times y, which is really L cubed times C. Okay, L cubed times C, which is equal to, in this case, we let k equal 2. This is equal to 2 to the fourth power, right? So then, if that's k, then what would L and C have to be? Well, wouldn't L and C both have to equal 2? Doesn't that make sense? If you're forcing k to be a certain value, wouldn't L and C also have to be approximately equal? So L is approximately equal to C. And this thing, which is approximately equal to k. So what's this thing going to look like? Well, if we do the L versus C line here, okay, we do the L versus C line, we let k, say k equal to 100. So let k equal to 100. Then 100, 100, we let L equal to 100 and C equal to 100. That's on this curve. Now that doesn't describe the whole curve though. Why? Because if k is equal to 100, then this thing is going to be 100 to the fourth power over L to the fourth power, or L to the third power. L to the third power is equal to C, right? Does it make sense? Like that's going to be, it's going to be pretty big numbers, but what you're getting is you're getting a rational curve. And what do rational curves look like? Well, they look like this. Okay. So what we're going to get is we're going to get a family of rational curves that look like this, but follow the line L equals C. Okay, they follow this line L equals C because what are we doing? We're fixing K. We're fixing K and we're saying, look, let K approximately equal C, which is approximately equal to L. So K is approximately equal to C, which is approximately equal to L, and then you can fix that. And then it gives us a general idea of what these level curves are going to look like. Okay? Because of the relationship between the powers. Here. Okay, it's counterintuitive, but it does work. Okay. So number 6. Okay, sketch the level curves for our friend z equals the square root of 9 minus x squared minus y squared. Okay. So again, this thing was the top of that sphere, right? We want to sketch the level curves. Okay, so let's see what happens when k is equal to 0. Okay. So let's let z equal k here. Okay, and see what happens. Okay, so we get the square root of 9 minus x squared minus y squared. Okay, and then we're going to square both sides, and we get, okay, x squared plus y squared plus k squared equals 9. Okay, and so x squared plus y squared equals 9 minus k squared. Right? Okay. So this is a circle of radius what? Of radius square root of 9 minus k squared, centered at 0, 0. Okay, that's that guy. So let's see what happens when we let k equal to 0. Well, what happens? Well, r is equal to 3. Okay, so when k is equal to 0, 1, 2, 3, 1, 2, 3, 1, 2, 3, 2, 3, then we get a nice circle. Let's go back. Let's get rid of this guy. Oh, it's not going to let me do it. Okay. There we go. 1, 2, 3. There. Nice. Okay, so this is k equals 0. Is that? Okay. Okay, what about when what else can we do here for this thing? Is there anything that's going to be nice? Okay, what happens when k is equal to 1? Then what happens? Well, we get radical 8. R is equal to radical 8, which is 2 radical 2, right? 2 radical 2. So what is that? That's 2.82, basically. Is that right? 2.82?
Yeah, I think that's right.
Okay, and so we get this radius of 2.82. Okay, again, my circles are going to suck, so apologize for my sucky circles already. Okay, but we get this guy there, and that's going to be k equals 1. Okay, what about k equals 2? K equals 2, that's going to be the square root of 5, which is what, 2.1 something? Let's see, 2 point square root of 5, 2.23. So 2.23. Okay, and so again, we're still inside this 2.23. Okay, boom. We're still inside that 2 mark. I need something that's going to draw some better circles, but you get the idea. Okay, so this is going to be k is equal to 2. We're still not inside that 2 mark, even at 2. Okay, well, what happens when k is equal to 3? That's when we go to 0. Okay, r equals 0. Boom, that's right in here. So we get these level curves. Okay, so this is when k is equal to 3. Okay, what does this tell me? It tells me that the rate of change is pretty fast until we get to the top, when the rate of change slows down. Okay, the rate of change is pretty fast from 1 to 2, from 0 to 1, and then from 1 to 2, and then from 2 to 3, the rate of change slows down as we get more of that dome shape. Okay, it slows down. Okay, so you're traveling. Okay, less height. You're going up less height in the same amount of vertical or horizontal distance. Okay, you're traveling less vertical distance. Okay, so. Okay, number 7. Okay. Okay, so sketch level curves. Of z equals 6 minus 3x minus 2y. Okay, and so we get, okay, k is equal to 6 minus 3x minus 2y. Well, this just becomes, if k is a constant, this just becomes the equation of a line. So these are level curves when z is equal to k. This is a plane, right? This is a plane. Right, so think of this as like a plane in space. Right, and if I were to slice these guys with respect to the z-axis, well, what would I create? Wouldn't I create lines? Does that make sense? If I'm slicing horizontally, as z goes up, okay, as z changes different values, then what are the slices through those planes horizontal to the xy plane? Well, those slices, those traces are just lines. They're just lines. Hopefully that makes sense. Okay, because you would slice these guys, right? You'd slice them. Okay, and so what's the intersection of two planes? Well, the intersection of two planes is a line. Okay. Whoa, come back. Okay, that's the intersection right there. just a rough sketch. But hopefully you get the idea. And these are the axes, by the way. Should probably not make everything the same color, but you get the idea, right? Okay. If you want to dash these, you can dash these too. Oops. Ooh, that was way too big. Dashing through the lines. Oh, that's not dashed. I don't know. Give it some nice perspective. Whatever. You get the idea. Okay, so K is just a constant, right? K is a constant. This is going to create lines. Let's just solve for Y. Okay, slope-intercept form. So we get negative 2y is equal to 3x plus k minus 6. Okay, divide by negative 2. Okay, and we get y equals negative 3/2 x plus k minus 6 over negative 2. Okay, that's my y-intercept.
Isn't it 2y?
Oh, is it 2y? Oh, wait. Yeah, 2y. Did I mess it?
It's 2y, not negative 2y.
Well, I tossed these guys to the other side. Did I not?
Oh, okay.
Does that make sense? I think I'm good. Okay. So this is my y-intercept over here, and this is my slope. Okay. And so what are we getting if we graph this thing? What are we getting? Well, we'll just get a bunch of parallel lines, right? Okay. For example, let k equal 0. What would k equal 0 be? Well, k equals 0 would just be this line. Right, through these 2 points. I'm going to use a ruler. I'm tired of not having straight lines. Okay, I would get this line. Okay, that's k equals 0. Or sorry, not 0. K equals 6, I should say. K equals 6 is this guy here. Gives me a y-intercept of 0. Okay, and k equals 6 will be here. Okay, what about, let's go up by 2's. So we get divisible by 2. What about k equals 4? That's going to be 1, right? 1. So that's going to be a parallel line to this guy through 1. Okay. So that's k equals 4. Okay, and then if we did 2, k equals 2, this would be positive 2. So it would be my y-intercept. So positive 2 would be the y-intercept. And this really isn't to scale. Okay, so that's 2, and then what would be at 3? At 3, sorry, when k is equal to 6, or sorry, when k is equal to 0, we would be at 3, right? We'd be at 3. So we're just going to get parallel lines for our level curves. Okay, parallel lines. With slope of negative 3/2. Okay, and we could call this a family of curves. Okay, it's a family of curves. Okay, functions of 3 or more variables Okay, functions of 3 or more variables. Okay. 8, find the domain of f if f of x, y, z is equal to the natural log of z minus y plus xy sine z. Okay. So what's the restriction on z, x, and y? Okay. Well, the only restriction on x, y, and z is that z minus y has to be greater than 0. Okay, or z has to be greater than y. Okay. So the way that we write that is we would say, that we would have the z is greater than y, and this wouldn't be a line, this would be a plane. Okay, why? Because the domain is 3-dimensional, which is kind of hard to think about, and the range is 4-dimensional. Usually when we talk about 4 dimensions, we will talk about time as the 4th dimension. Okay, but the domain is 3-dimensional here. So this is actually a plane. Okay, this is a region bounded by a plane. Region bounded by the plane z equals y. Okay, that's the region bounded by that plane, z equals y. Okay, and it's everything above that plane. That's the domain. Okay, so the way I'm just going to write that is in set notation. So the domain is x, y, z, such that it is an element of R cubed. Okay, it is an R cubed, such that z is greater than y. Okay, so the domain is in R cubed. Okay. Okay, so the original graph of f is in R4. Okay, but the domain is R3. Okay, is R3. Okay, analogous to level curves of a 3-dimensional function. Dimensional function. I'm trying to write too fast. Function. Okay, analogous to level curves of a 3-dimensional function. Okay, mapping to 2-dimensional space curves, or sorry, yeah, 2-dimensional level curves, I should say. Level curves. Okay, are 4-dimensional functions mapping to 3-dimensional level, and we call these level surfaces. Okay, level surfaces. nothing but level surface. Okay, so let's look at this here. We have f of x, y, z is equal to x squared plus y squared plus z squared, right? So for a level surface, okay, let f of x, y, z equal k for level surfaces. And so what's that going to do? Well, this is going to be give me level surfaces, okay, where r is equal to radical k, right? So these are spheres of radius radical k. Okay, they're spheres of radius radical k. Okay, so what would this look like? Well, again, this is level surfaces, and we can think of the function changing maybe with respect to time. Think of this maybe as t. Okay, like we're changing. The fourth dimension here is time. Okay, and so when t is equal to a certain value, or when k is equal to a certain value, k equaling t. Okay, when k is equal to t, t is equal to a certain value, then we're at a certain size sphere. Okay, we'll say that t was equal to 0. Where would we start? We would start at a point 0, 0, 0. What happens when t is equal to 1? Okay, or in this case, k is equal to 1. Okay, I'll just do t to make it easier. Okay, let this equal t. Okay, t, boom, there we go. Okay, just know that k is equal to t. Okay, so when t is equal to 0, boom, we're right there. Okay, we're at a dot. Okay, when t is equal to 1, where are we at? Well, we're at a sphere of radius 1. Right, we're at a sphere of radius 1. Okay. What happens when t is equal to 4? What happens 4 seconds later? Where are we at? We're at a sphere of radius, or sorry, 3 seconds later. 3 seconds later, we're at a sphere of radius 2. Right? So we're now at a sphere of radius 2. Okay, what happens when t is equal to 9? Well, now we're at a sphere of radius 3. Okay. Get the idea? Okay. So it's expanding, right? As t increases, the level surfaces expand to become greater spheres. Okay, they're spheres. They're not balls, they're spheres. They're just the surface, just the three-dimensional surface. Okay, they're just the surfaces. They're not anything inside these spheres. Okay, a sphere is everything on the outside. A ball is everything on the outside and the inside. Okay, just like this is a circle and this is a disc. This is a sphere. This is a ball. Okay, see the difference? No, you're like, yeah, it's clear as mud. Like, well, there you go. Okay, you're in good shape. Okay, so these are just spheres, okay, of different radius. It's center at 0, 0, 0, okay, with radius radical t. Okay. Okay. So now that everything is confusing, we'll just leave it there and we'll go on to something else, okay? Like whatever. Clears that right up. Let's go on to something a little easier. Limits and continuity in 3 dimensions. 3-dimensional space, limits and continuity. You're like, this is easier? I don't know. It's easier for me. But that's because I don't like getting bogged down in all these, you know, wacko graphs. Okay, but like, whatever. I think it's easier, but it's what we're setting up here is eventually we're going toward something called partial derivatives. We got to talk about the limit first because a derivative is a special type of limit. So we're going to do multivariable calculus. We got to get to the calculus. Okay. We got to get there. The way we get through to calculus is through limits. Okay, let f be a function of 2 variables whose domain D includes points arbitrarily close to AB. Okay, includes points arbitrarily close to AB. Then we say that the limit of f of xy as xy approaches AB is L, and we write the limit as x approaches a comma b of f of xl of fxy is equal to L. Okay, so we're approaching A and B simultaneously in this 3-dimensional function. Okay. So why is it a 3-dimensional function? Because it's an f of xy. So f of xy is z, right? So you're approaching z, okay? Approaching a value of z, but you're doing it from the x and y direction. Okay, saying what's x approaching, what's y approaching at that value of z. Oh, sorry, this should be x, y is approaching AB. Okay. Okay, and this is true. This is true. Comma, let's put a comma in there. And we say that the limit approaches L, okay, if for every number epsilon greater than 0, there is a corresponding delta greater than 0 such that if xy is an element of our domain and 0 is less than the square root, okay, of x minus a squared plus y minus b squared, the distance between a and b, is less than delta, but it's greater than 0. There's got to be some gap there. Then the absolute value of the function minus its limit is less than epsilon. So we're basically just setting up a delta epsilon definition of what the limit is. And again, we're just saying, look, okay, as we approach this point out in space on this function, okay, on this f of xy, and we haven't really talked about what f of xy is at this point, but it really is, think of it kind of like this surface, okay, okay, and you have this point out in space, right? And we're saying that as we approach x, this point from the x direction and from the y direction, okay, then the difference between, okay, what it's, the distance between the xy column, let's have 2 points here. Let's have 2 points, okay. So this is a point not on the curve. Let's have the other point not on the curve. Okay, and then we're saying, look, this is, okay, this guy here is AB. And this guy here is XY. Oops. Let's make that smaller. Okay. Well, this is another point on the curve. XY will be on the curve. That's fine. Okay, but they're getting arbitrarily closer and closer to each other is what we're saying. Okay, and this is going to approach this guy. Okay, I'm pushing this point closer to this point, and it's traveling along an x path and a y path to do that. Okay, it's traveling in the xy plane, so x's are changing and y's are changing. Okay, and it's getting closer and closer to AB. And so the difference between the z value at this point and the actual z value at the point AB is also getting closer and closer. So if the distance between xy and AB is closing by delta, then the distance between z and L is also closing. That's all it means, okay? That's epsilon, not E. Just saying, look, as I get close, as D gets smaller, as delta gets smaller, epsilon gets smaller. And I can fix an epsilon, I can always fix an epsilon that's getting closer and closer and closer and closer. And so we just say it's the limit. It's always going to get closer and closer and closer. Right? Okay. So let's do an example. Make this a little clearer. Okay, show that the limit of xy approaches 0, 0 of x squared minus y squared over x squared plus y squared does not exist. Okay, why does this not exist? Okay. Okay, so if y equals 0, if we approach this, okay, along the x-axis, let y equal 0, right? Y equals 0. Okay, is that? Let's think about this for a second. What happens when y is 0? Okay, when y is 0, okay, that means that x is allowed to move, but y isn't, right? And so what does this mean? It means that we're approaching we're fixing y equals 0, and we're approaching 0, 0 along the x-axis, right? And if we approach 0, 0, approaching 0, 0 along the x-axis, right? Because we fixed y. We said y can't move. It's y is 0. Okay, so we're saying that if you let y equal 0, boom, fix y there to be 0, then what happens? Well, then we get the limit x0 goes to 0, 0 is equal to, or of 0 squared, or sorry, x squared minus 0 squared over x squared plus 0 squared, right? Okay, what is this going to be? Well, this is just going to be x squared over x squared, which is 1. Does that make sense? Right? The limit of that value is going to be 1. So the z value is 1. So I'm really kind of approaching it like this. Again, it's kind of hard to draw. Let's see. But I'm approaching it. It doesn't matter where I'm at, but I'm approaching this thing. Okay, and I'm going to hit f of xy equals 1, right? If I approach it along the x-axis. Okay. What happens if I approach it along the y-axis? Let's do the opposite here. Let's approach this thing along the y-axis. Let's come in here from this direction. Then what happens? We'll say the limit, okay, as x is 0 now, but y is allowed to vary, of x squared minus y squared of x squared plus y squared. Well, plug this in, right? So these go to 0. And so what is this equal to? Well, this equals -1 this time. And so we're going to end up down here below at -1. So we're just, and what does it mean when I approach the value from two different directions, and we get we get to this, we're approaching the same point, but they don't meet. What does that mean? Well, in 2 dimensions, what did that mean? That mean that, ooh, look, I'm approaching here, and I'm approaching here. I'm approaching the same value. What's the value? I'm approaching x equals 0, right? And what happens? What happens when I approach and they don't meet up? Well, the limit does not exist. Does that make sense? There's a fly in here. Kill it. Get on my room floor. Okay? Does that make sense? That in 2 dimensions, it looks like this. In 3 dimensions, it looks like this guy, right? We don't know what's happening with these things. They could be all wacko. Okay, but we do know that if we follow along those trajectories, they're going to miss each other. They're going different places. Okay, even though they're approaching the same spot, the same x and y value. They're approaching 0, 0. They're just, we fix 1. Okay, since f has 2 limits, then the given limit does not exist. Okay, not the same. Not equal. So the limit does not exist. Okay, does not exist. Okay, good times. These are good times. Fun stuff. Okay, number 2. Okay, if f of xy equals xy squared over x squared plus y to the 4th, okay, does the limit exist? Does the limit exist? Okay, does the limit exist for this function? Okay, which limit? Does the limit as x of y approaches 0, 0 let's do 0, 0 again, of the function, okay, of xy squared over x squared plus y to the fourth. Does this exist, right? Does this exist? Do all roads lead to the same spot? This is what I'm asking. Okay. So let's test. Let's test. Let's test f of x0. What happens when we let x be 0? Oh, this thing equals 0. Okay, that's cool. Okay, what happens when y equals 0? I mean, when we let y equal 0, the thing goes to 0. When we let x equal 0, the thing goes to 0. Okay, so that's kind of cool. Okay. However, not all roads lead to 0. Okay, not all roads lead to 0 here. Kind of sucks. Okay, what if we let x be equal to y squared? Okay, let x equal y squared. What does that look like? Okay, x equals y squared. So if we let x be 0, let's draw this out. Okay, if we let x be 0, then we definitely go to 0, 0. If we let y be 0, we definitely go to 0, 0. However, if we let x equal y squared, which is, okay, which is this guy here, x equals y squared, that's this guy here. That's this parabola. Oops. Parabola. Okay, we get problems. Why do we get problems? Well, let's see. Let's see what happens when we get this. Let's plug this in. Let's go f of y squared comma y is equal to y squared times y squared all over y squared squared plus y to the fourth. Okay. So this is going to be equal to y to the fourth over, this is going to be 1y to the fourth plus another y to the fourth, that's 2y to the fourth. Cancel, cancel, we get 1/2. Look at that. We approached 0, 0, but where did we end up? We ended up with z equals 1/2, which is above 0. So yeah, the limit does not exist here. Okay, so it's much easier to prove something doesn't work than something does work, right? Because what do you need to prove something doesn't work? To prove something does not work, requires a single blank. What's the blank? What's the blank there? To prove something doesn't work requires a single what? A single lady? All the single ladies? All, what? Oh, you know what? Never mind. I can't hear anybody. Is anybody talking to me? Long, are you talking to me? I don't know if you're talking to me or not. I have to see. No? Oh, maybe it's just down too much. Nope. There's the magic.
Professor, is it proof?
Nope. It's not a proof. That's the other side of the coin. To prove something doesn't work requires a single what?
A justification, maybe?
A single justification on why it doesn't work?
Oh, never mind.
If something doesn't work, it requires a single what?
Like a single piece of evidence, maybe?
No. Okay, it's much easier to prove something doesn't work than something works all the time. Yeah, thank you, Long. It is a counter example. Very good. It's a single counter example. Isn't that what we've been doing here? A single, when we get it, once we get a single counter example, don't we have to, can't we stop? Right? It's much easier to prove something does not work because it requires only one counter example that it doesn't work. So I'm going to give Long extra credit for that. Long gets extra credit for that. I don't give extra credit in my class, but today I will. Okay, let's write that as a note for myself. Okay, yes, it's a counter example. Okay, it requires only one counter example. Okay, to prove something does not work requires a single counter example. To prove something holds true all of the time requires a mathematical blank. Was that? Somebody already said it.
Proof.
Yeah, proof. Very good. Okay, thank you. Proof. I'm not giving extra credit for that one because somebody already said it. Okay, so to prove something holds true all the time requires a mathematical proof. So let's look at the next one here. Okay, so we want to do, okay, number 3, find the limit of xy goes to 0, 0, okay, of 3x squared y over x squared plus y squared, if it exists. So let's see if this thing, if we can find a counter example here. Okay, let's see if we can find a counter example. Then we're done. Don't worry about it. Okay, if let's do f of x0, that's just 0, right? Everything goes to 0. F of 0y, that's just 0. Let's put in some some x's as equal to y's. So let's do f of, okay, y. Okay, let's let x equal y here. Okay, then this becomes 3y cubed over 2y squared, which is 3 halves y. Okay, but we're saying that we want this thing to go to 0, 0. So y is going to 0. Okay, so as y goes to 0, okay, if we say that, if we take this is along, okay, we're approaching 0, 0 along the line y equals x, okay. Okay, and so we're going to say that this is equal to 0, okay, since y is approaching 0. Okay, since y is approaching 0, we can get there. We can get there along this line y equals x. So what would this look like? Okay, it would look like, okay, where's the line y equals x? Well, the line y equals x is right here. And so what are we approaching 0, 0 on? We're approaching 0, 0 on this line. And where's the function value at that point? It's 0. Why? Because we're approaching y is equal to 0. We're just doing it along the line y equals x here. Okay, along the line x equals y, I guess you could say. Okay, either way. Okay, so this thing goes to 0. That thing goes to 0. That's nice. Okay, let's get a little spicier. And let's say that if we let this be any line, not just the line y equals x, but let's let this be the line y equals mx. Okay, y equals mx. Let's do that one. f of x, mx, is equal to what? Well, let's plug this into our original function. Where's our original function? Right there. So this is going to be 3x times mx squared all over this is x. X squared plus mx squared. Right? So what's this going to become? This is going to become 3m squared x squared over, this is going to be m squared x squared. So I'm going to factor out the m squared. Okay. So I'm going to get the, this is going to be m squared plus 1 times x squared, right? Okay. So then the x squareds cancel out. Okay. Wait a second. No, they do not cancel out because I left off an x. This is 3x m squared x squared. There we go. Okay, these x squareds cancel out. What I'm left with is 3m squared over m squared plus 1 times x. But because there's an extra x there, okay, as we approach along any line, along any generic line, aren't we still approaching 0? Like x is 0? Yeah. Where x is approaching 0, right? So what's that x going to go to? It's going to go to 0. So the whole thing, this whole thing goes to 0. Goes to 0. So it seems like no matter which path I take, okay, all paths lead to 0. Which, no matter what path I try to take here to 0, if I come in this way, if I come in this way, if I come in this way, all paths, okay, we already saw that way, and any line, any linear path is going to, okay, we could say, well, what about any quadratic path? What about any of those other paths? And then we get a bunch of, scenarios, okay, but it looks like all roads lead to 0, okay? To 0. Well, we can't just say we've tested every single one of them because we haven't. So, okay, so we would have to do a proof. Okay, so let's do a proof here. Let's do a proof. Okay, proofs are fun. Proof. Prove what? Prove that the limit as xy approaches AB, okay, is it AB or is it 0, 0? It should be 0, 0. Sorry. Should prove that it should be 0, 0, not AB. Okay, limit as xy approaches of 3x squared y over x squared plus y squared, that equals 0. I want to prove this. Okay, let's prove this. Prove it, people. Prove it. Okay. So let epsilon greater than 0. Okay, let epsilon be greater than 0. Then we want delta greater than 0 such that if 0 is less than square root of x minus a squared plus y minus b squared is less than delta, then the absolute value of f of x minus L, f of xy, minus L is less than epsilon. Boom. That is, okay, 3x squared y over x squared plus y squared minus 0 in this case is less than delta. Well, I don't want to skip this. Let's not skip this. This is too important. That is, if, put in the if 0 is less than the square root of x minus 0, okay, this thing's going to 0, okay, that's what a and b are here, going to 0, 0, okay, if this thing squared plus y minus 0 squared is less than delta, then the absolute value of 3x squared y over x squared plus y squared minus 0 is less than epsilon. Oh, okay. That's good. Okay, so what is this? Can we clean delta up at all? Can we clean up delta here? Well, yeah. So 0 is less than the square root of x squared plus y squared, which is less than delta. Okay. Well, that's good. Okay. Then we get this thing here. But can we clean this thing just means implies. I don't know if you've seen this before. This means implies. Okay. This is your if and then, right? If implies then. Okay, that's just an arrow. Okay. That means implies. Symbolic logic. Okay, this thing will imply what? Well, let's clean this guy up. Well, this is the absolute value of 3x squared y over x squared plus y squared is less than epsilon. Okay, so again, I'm going to bring this down. This thing here, x squared plus y squared is less than delta, implies what? Well, we've got a lot of squareds here, and these squareds, they kind of like, if I take a value and I take the absolute value of a squared, it's the same value. Okay. Right? So if I took, say, the absolute value of the top here and the absolute value of the bottom, well, would I really need the absolute value of the bottom? Well, no, I really wouldn't. Okay, because any x or y value squared and added together would still be positive value. So the way I'm going to rewrite this is this thing here. It's going to go 3x squared absolute value y over x squared plus y squared. Oh, okay. It's less than epsilon. Okay. Interesting. Okay, let's get epsilon in terms of delta. Okay, how can we get epsilon in terms of delta? Okay, that's the idea here. Well, okay. Let's think about this for a second. Okay, we're going to do something kind of sneaky here. Okay. Okay, and we're going to say that this thing here, this 3x squared, okay, 3 absolute value y, and I'm going to call this x squared over x squared plus y squared. Okay, I'm going to say that is less than or equal to this is always going to be less than or equal to 3 absolute value y. And why is that true? Well, because we have a ratio, right? A ratio of a value squared over the value squared plus another value, which is always positive. And so if we take a number, say that the number was, I don't know, 9, and we take it 9 on the bottom and we add to it anything, well, and this is a positive number, right? Add to it any positive number, then what's the result? Well, that's always going to be less than, right? Less than or equal to 1. Does that make sense? Okay, that's always going to be less than or equal to 1. Okay, so this x squared over x squared plus y squared is always less than or equal to 1. Oh, okay. Oh, okay. It's bigger than 0, less than 1. Okay, make sense? Okay, so we'll say that that is less than this. Okay, but I'm going to rewrite this as, okay, as this thing is less than that, but that's equal to 3 times the square root of x, or square root of y squared. Square root of y squared. Okay, square root of y squared. Okay, now is that the same? Yeah, that's the same. Absolute value, the net result of squaring and square rooting is the absolute value. Okay. Okay, and I'm going to say that this thing is then, let me get rid of this. Let me make it a logical statement here, because I'm getting crunched. Okay, that's, okay, I can keep going down here. This is equal to 3, oops. This is equal to 3 times the square root of y squared, which is then less than or equal to 3 times the square root of x squared plus y squared. Ooh, that looks good. Okay, which is then less than, a hard less than, 3 delta, right? Why? Because the square root of x squared plus y squared is less than delta. Oh, okay. So follow the logic here. The original was less than or equal to 3 absolute value of y, okay, since x squared over x squared plus y squared is less than or equal to 1. Okay, and then this is equal to, which is less than this thing if we add anything, which is then less than, and this should say, this should move down a line, since, okay, the square root of x squared plus y squared is less than delta. Okay, boom. So what's the net result? The net result is that we have 3 absolute value of y, x squared over x squared plus y squared, is less than 3 delta. Oh, okay. So what do we know? So we know that epsilon, okay, is equal to 3 delta. Boom, there you go. Okay, so let epsilon equal 3 times delta. Okay, and we can now prove this. Okay, so if we let epsilon equal 3 delta, I get to say if we let epsilon equal to 3 delta, then the statement is proven or provable. Okay. I'll just put proven. Okay, so how is it proven? Okay, so the first part is to find your epsilon. In a delta epsilon proof, you got to find your epsilon. Okay, in terms of delta. Then you can go into the real. This is kind of what I call the discovery phase. This whole thing right here is the discovery phase. Discovery of what the hell is epsilon. Okay, that's the discovery phase of the proof. Every single mathematical proof that involves delta and epsilon, it has a discovery phase. It's basically you're trying to find what the hell epsilon is. Okay, what is a good epsilon that I can use? That's the discovery phase. Once the discovery phase is over, we're like, yay, we went through all that work to find out what epsilon was equal to in terms of delta. Okay, now that we did all that work, now we can actually go into to the formal proof. Okay, so formal proof. You're like, I thought we were already in the proof. Well, we were kind of, but we just had to figure out what delta was, or sorry, what epsilon was in terms of delta. Then we could actually write it up as a formal proof. And we say thus what? Thus, if 0 is less than or equal to, or sorry, it's hard less than. If 0 is less than x squared plus y squared is less than delta, then, okay, then what? Okay, remember, well, what was the original statement that we wanted? We wanted to say let epsilon be greater than 0. Then we want delta greater than 0 such that if this, then this. Oh, okay. So we're saying that if we let AB go to 0, 0, okay, as xy approaches 0, 0, does the function minus the limit approach, you know, my epsilon? Okay, so as those values get closer and closer, does the limit and the function get closer and closer and closer together? Okay, thus if this thing holds, then what do we know? Then the absolute value of 3x squared y over x squared plus y squared minus 0 is less than epsilon. Okay. Okay. So we want to prove that. Well, let's prove that. Let's now go forwards in this. So what does this equal? This equals, we saw this was 3x squared absolute value y over x squared plus y squared. That's easy. Okay. Which is again less than, we're just going to kind of restate what we're doing here. Okay, which is less than or equal to 3 times the absolute value of y, okay, which is then equal to 3 times the square root of y squared, which is then equal to, or sorry, which is then less than 3 times x squared plus y squared, which is then less than 3 delta. And what do we say 3 delta was? 3 delta was epsilon, which is equal to epsilon. Okay, so what? So what did this prove? It proved that if we let the function minus the limit, okay, the function minus the limit does go to epsilon. Okay, does equal epsilon. Oh, okay, that's cool. Okay, so given that this value for, I mean, if you really wanted to, you could say that, look, we proved that 3 delta was equal to epsilon. Therefore, this is kind of what they do. They kind of do it backwards in a lot of proofs. Then they say that, well, divide by 3 and we get delta is equal to epsilon over 3. And so then, well, what is delta here? We could go a second step here if we really wanted to. We say, oh, 3 is delta is equal to epsilon over 3. Therefore, the 3's cancel out and we're left with epsilon. Boom, proven, done. Okay, just shows that the universe holds. So the absolute value of 3x squared y over x squared plus y squared minus 0 is less than epsilon. Therefore, the limit as xy approaches 0, 0 of 3x squared y over x squared plus y squared is equal to 0, and end of proof, QED. Put my little square. That means I'm done with the proof. I've proven it forwards, backwards, sideways, that it will always work. Okay, let's just set up the definition of continuity real quick, and then we'll call it a day. Okay, continuity. Okay, a function. This is basically the same thing in second and 2 dimensions as it is in 3. Okay, a function f, okay, is continuous, or f of, we'll say of two variables, okay, is continuous at AB, okay, if, okay, the limit as x, y approaches AB of f of x, y equals the function evaluated for AB for all x and y. Okay, then, okay, then it's continuous at that point. But what if we want to talk about a continuous function? Then we say that f is continuous along its domain in D. D is its domain. Okay, or we say on D. On D, its domain. Okay, if f is continuous at every point A, B, in D, okay, and its domain. Okay, so if we think about, okay, polynomial surfaces, okay, just like polynomial functions were continuous in R2, okay, polynomial surfaces are continuous in R3. Okay, so if we kind of extended this out, okay, this is like a sheet, okay, maybe a sheet of metal or something, right? So these are polynomial surfaces. They are also continuous. Okay, just kind of extend it out, your understanding there. Okay, so let's do 4 and 5 real quick. We've already done all of the heavy lifting for this. Okay, is g of x, y equal to x squared minus y squared over x squared plus y squared, okay, continuous US at 0, 0. Well, does the limit exist? We need to know if the limit exists, and then we need to know if the function is the same as the limit. Well, if we go back to example 1, example 1 says that the limit does not exist. The limit as x, y approaches 0, 0 of this thing does not exist, of g of x, y. G of x, y does not exist, so therefore, no. Okay, no, not continuous at 0, 0. Okay, it's not going to happen. Okay, why? Because we need the limit to equal the function. Okay, we would need the limit to equal the function. Okay, and if it's not going to, it should be AB. Okay, and if it's not going to, then we're done. Let's do the last one here real quick. 30 seconds on the clock. Okay, so does this thing exist? Okay, is f of xy equal to 3x squared y over x squared plus y squared continuous at 0, 0? Well, what was the limit as xy approaches 0, 0 of this function of f of x, y? What was that? What was that? Anybody know? Anybody know? What's the limit? What's the limit of this function?
It was 0
Yeah, how did you know, Armando?
because we proved it.
Yeah, because we just spent 45 minutes proving that, right? That was bad. We just spent, see example 3, see proof. Okay, boom. But what else is true? Isn't f of 0, 0 equal to 0? Isn't that also true? So is this continuous? Yes. Boom, done. Look at that. And that's it. That's all I got. It's time to go. Okay? Good stuff. Okay, I'll see you guys on Wednesday.
Bye. Thank you.
Sure.
Thank you, Professor.
Yeah. Oh, thank you, Ashley.